Okay, today we're going to be talking about hydrolysis. This is a pretty important unit in acids and bases, or subject rather. So to start right off, let's talk about water. Water molecules are constantly moving and bumping into each other, and when they do, one of them breaks and you end up with hydronium and hydroxide. Now, both of these are present in equal proportions, so that's why water is neutral, right? Because the concentration of these two, when this happens, will always be equal. And as we talked about before, we know that when you have an acid, that's when your concentration of your hydronium is greater than in your base. And if you have a base, it's the opposite. Okay, so this is happening, and so that's why in aqueous solutions we always have the hydronium and the hydroxide. And we also learned that acids, the formulas for acids will typically have the hydrogen deliberately placed in the front of the formula. When we draw this equation, this dissociation equation, this happens, and our first definition of an acid is something that produces H plus in solution, which of course H plus and H3O plus are effectively the same thing. So we refer to that as hydronium. But sometimes you have acids, things that are acidic that don't look like acids. Here's one example. NH4 plus is called ammonium, and ammonium is acidic because it meets the definition of producing H plus in solution. Because H plus is now floating around, the pH is lowered, and this is an acidic solution. So NH4 plus is an acid. Other ions in water that don't look like they're acidic but are can be found in salts. So let's back up for a section. Let's talk about the definition of a salt. Salt is any ionic compound without H plus, OH minus, or O2 minus. Okay, so it can be an ionic compound, but it can't have one of those three things. So your most common example is NaCl. That is called table salt, and whenever people say salt in a conventional sense, they know people that are talking about sodium chloride. But it's not the only salt. This is a salt, potassium iodide. This is a salt, potassium or calcium nitrate. Right? These are all salts. So if I have a compound like this, copper chloride, that's a salt. However, if we measured the pH of this solution, we would get a pH less than 7. So that means this is acidic. So we would need to know why. So as it turns out, the copper ions, and there's actually 4 of these ions, we'll just kind of outline them here: copper, zinc, aluminum, and iron. These first 2 have a charge of +2. These last 2 have a charge of +3. The easy way to remember these is cousin alpha. If you just kind of read the element symbols phonetically, cousin alpha. Okay, these cousin alpha ions are acidic, and here's why. The copper, when it's dissolved, will attach to 4 water molecules, and the formula looks like this. Because water is neutral, the charge stays the same as it was when it started. So it started as a +2 ion. You attach 4 waters, and it's still +2 overall. So this in and of itself is not all that interesting. Here's the copper ion. If we were to draw a picture, here's the water, 4 of them. Notice how the oxygen side is the one that's attracted to the positive cation. However, I'm going to make this last hydrogen a different color. This formula, this molecule ends up breaking. And when it breaks, let's go ahead and duplicate this. When it ends up breaking, the different colored hydrogen pops off. So if it pops off, that makes this acidic. So what happens to the formula after that H comes off? Well, there's still copper. There's no longer 4 waters. There's now 3 waters that are complete. But the fourth one, which the one that broke, let's make that a different color to stand out. That is not a water anymore, so that's why there's not 4 waters. That's why there's just the remains of the fourth. Now, anytime an H plus leaves, the charge goes down by 1. So we started with a charge of +2, but it ends up being a charge of only +1 because your other positive charge is the hydrogen ion. So this reaction explains why we have copper ions, zinc ions, aluminum ions, and iron ions that end up being acidic in solution. It's because of this combining with the waters where one of the waters releases an H+. So it's kind of a weird thing, but if we think about what hydrolysis is, if we go back, I didn't even define, let's define hydrolysis. The hydrolysis is the reaction with water to produce hydrogen ion or hydroxide. So when you don't understand where an H plus or where an OH minus came from, that means hydrolysis took place. The OH minus or the H plus came from water, and that's why something is acidic or basic. Okay, so to summarize the positive ions that are acidic, really these are 5 that you have to commit to memory: cousin alpha and ammonium. So that explains acids and explains positive ions. Let's talk about basic ions. So let's say I have this salt, Na2CO3. If I test the pH of this is going to be basic, but let's talk about why. This salt splits up into 2 different ions. We get the carbonate ion and we get the sodium ion. Now the sodium ion is inert. Inert means non-reactive. It doesn't undergo hydrolysis. And the way that I know that is because the sodium ion is derived from sodium hydroxide, which is a strong base. Any ion derived from a strong base is in and of itself inert. So if we think about what all the strong bases are, we have LiOH, NaOH, KOH, you have calcium hydroxide, strontium hydroxide, and barium hydroxide. So these ions here, if they are found in a salt, then those 6 are inert ions. And that's really the reason why you need to know the list of strong bases and strong acids, because you have to be able to tell if an ion is going to be inert or not. So the easiest way to know that is to memorize the strong acids and strong bases. Okay, so since sodium is inert, what about the CO3? What about this guy? Well, negative ions will undergo hydrolysis with water as long as they're not derived from a strong acid or strong base. So this looks like this. Carbonate ion ends up attaching to hydrogen ion and pulling it right off of water, and this is what results. We got hydroxide formed, which means this was a basic ion. Carbonate was a basic ion. Let's try another. So here's a salt, barium cyanide. This will separate and give us two ions, Ba2 plus, Cn minus. And we should recognize that barium 2 plus is inert because it's derived from a strong base, which means it's not going to do anything. So the next question is, what about Cn? Cn is not from a strong base. It is negative, so it will react. And when it reacts, it has to produce hydroxide. So this is what we get. So negative ions are generally basic, except those from strong bases. So just to give a couple extra practice examples. So let's say, here's one. We'll do aluminum bromide. We'll do, let's see, lithium sulfide, ammonium fluoride, strontium nitrate. Okay, so go ahead, pause the video here, and then see if you can work out whether these are going to be acidic or basic. Okay, so now that you've completed these, let's go ahead and reason out what's going to happen. So in the first one, aluminum bromide, what we should realize, these two ions, is that aluminum is a cousin alpha, which means that's going to be acidic. Bromide is derived from the strong acid HBr, which means the bromide ion is inert. So the only thing here doing anything is aluminum. Okay, so aluminum, being cousin alpha, is going to bind to waters. Now, unlike the last example, which had a charge of +2, this has a charge of +3, which means there will be 6 waters to start with. So your first equation looks like this. But then the second part of the equation, one of those waters breaks, and if one breaks, you no longer have 6, you have 5 complete waters, and you have the remains of the 6th water. The charge will go down by 1 as it releases an H+. So this is the result that I would expect you to write to justify why aluminum bromide is acidic. Okay, let's do the next one, lithium sulfide. Lithium sulfide, lithium is from strong base, which means it's inert. Sulfide is not from either a strong acid or strong base, and it's negatively charged, which means it will react with water. So because OH minus has to be made, the H attaches to the S2 minus and becomes S with a -1 charge. That's why S2 minus is basic. For the next one, ammonium fluoride, we have NH4 plus, we have F minus. Neither of these two ions is derived from a strong acid or strong base. So neither of them are inert. We have ammonium, which if you recall from earlier, we said you just have to memorize as an acid. Well, there's it forming H+. Fluoride, being a negative ion, should react with water to produce hydroxide, and to do that, it takes up the H+. So here we have something where one ion forms H+, the other ion forms OH-, and you actually don't know which one of these is better at doing its job. You don't know if the NH4+ is better as an acid compared to the F- as a base. So when both of these produce H+ and OH-, it's not neutral because, again, you don't know which one is stronger, so you have to say that this is unknown. The only way to know for sure is to test it with an indicator, with like a piece of pH paper. Okay? Here's the last example. So SrNO3 Sr2+ is from the strong base SrOH2, which means Sr is inert. NO3- is nitrate, which is from nitric acid, HNO3, which is a strong acid, which means this is inert. So this reaction is simply inert, no reaction. So if there's no reaction, if there's no hydrolysis reaction in water, then the pH of water will stay the same, which means this is going to be neutral. Okay, so that's the gist on hydrolysis salts and how to tell if they're acidic or basic.